Every matching system has the same nightmare. Students and hospitals, kids and schools. Two columns of wishes, one set of pairings, and somewhere in it, a rogue couple. A student and a hospital who like each other more than the partners they were assigned. They defect. Their abandoned partners repair. New rogue couples appear. The market unravels. In 1962, two mathematicians published a procedure that kills every rogue couple before it forms, guaranteed, every time for any wish lists. It now assigns tens of thousands of doctors to hospitals every March. It also hides a secret. The algorithm plays favorites, and it favors whoever does the asking. Set the stage precisely. Two groups of equal size. Everyone ranks everyone on the other side. A complete, honest wish list. A matching pairs them one-to-one. Call a matching stable if no rogue couple exists. No pair, across the aisle, who would both rather be together than with their assigned partners. Stability is the modest goal, not happiness, not fairness. Just no two people with both the desire and the ability to defect. The question, does a stable matching always exist? And can we find it? First, feel the danger. Pair people at random. In our simulated market of 100 aside, a random matching carries hundreds of rogue couples on average, hundreds of fault lines. Let one defect, repair the jilted, and the chain reaction begins. There is no promise it ever settles. Greedy fixes fail too. Repairing one rogue couple routinely creates two more. What's needed is not a patch but an architecture, a process whose ending state cannot contain a rogue couple at all. Here is the whole algorithm. Each round, every free proposer knocks on the door of the best name not yet crossed off their list. Each receiver looks at their suitors plus their current partner and keeps only the best, rejecting the rest. Rejected. Cross off that name, knock next door. Watch it on three couples. Proposals fly, one heart is traded up, a rejection bounces to a second choice, and after 6 proposals, silence. Everyone is engaged, nobody is knocking. That silence is the algorithm's exit, and, as we'll see, it's proof of peace. Why must it end and why in peace? It ends because lists only shrink. Every proposal crosses off one name forever, at most n-squared knocks, then silence. It ends in peace by a two-line argument. Suppose a rogue couple existed. He prefers her to his final partner. But he proposes in strict order of desire, so he must have knocked on her door somewhere along the way. And she only ever trades up. So, if she let him go or turned him away, she held someone she liked better, and her partners only improved after that. She cannot prefer him now. Contradiction. Rogue couples are not removed. They are impossible. Stress test it by machine. 100 proposers, 100 receivers, 50 markets with random wish lists. Result, 50 stable matchings, 0 rogue couples in any of them, confirmed by brute force checking all 10,000 possible pairs every time. The bookkeeping is light, about 490 proposals per market, 5 knocks per person, to tame a market with more possible matchings than atoms in the universe. Guaranteed stability, near-instant speed. This is why real markets run on it. Now the dark secret. Who wins? Same market, same honest wish lists. When side A proposes, side A's average partner sits around rank 4 of 100. Nearly everyone gets a top 5 choice. Side B's average, rank 20. Flip the roles, same lists. Side A crashes from rank 4 to rank 27. The mathematics is exact. Proposer side optimality. Among all stable matchings, proposers get the best possible, receivers the worst possible. Rejection is the price of asking, but the asker sweeps the board. In any matching market, the first question is, who gets to propose? Second secret, lying. Can you game the system by faking your wish list? If you are a proposer, no. Truth-telling is provably your best strategy. No fabricated list can win you a better stable partner. If you are a receiver, yes. A receiver who strategically rejects can sometimes engineer a better outcome. This asymmetry is not a footnote. It decides real design. When hospitals proposed, students could be hurt by honesty. The modern residency match was rebuilt so that students propose, making honesty safe for the applicants. The history has a twist worthy of the theorem. Gale and Shapley published in 1962, a paper so elementary it proved every claim without symbols, in a journal for teachers. Then economist Alvin Roth dug into the American residency match, the NRMP, running since 1952, and found its handcrafted clearing procedure was the Gale-Shapley algorithm, invented by committee, a decade early, with nobody knowing what it was. The theorem existed in the wild before it existed on paper. Markets under enough pressure evolved toward stability. Mathematics just wrote down the destination. Then the theorem started fixing the world. New York City High Schools, 2003. A chaotic application scramble replaced by a student proposing match, 30,000 fewer unassigned students in the first year. Boston school choice followed. Kidney exchange. Patients with willing but incompatible donors, arranged into swap cycles by stability logic, thousands of transplants that otherwise would not exist. In 2012, Shapley and Roth received the Nobel Prize in Economics, one for the theorem, one for the plumbing. Gale had died 4 years too soon to share it. One last twist, drop the two-sidedness. 4 students, 2 dorm rooms, everyone ranks everyone. Same rules. Here are wish lists where every pairing fails. Match 1, 2, and 3, 4. 2 and 3 defect. Match 1, 3, 2, 4. 1 and 2 defect. Match 1, 4, 2, 3. 1 and 3 defect. All 3 possible pairings. Each one carries a rogue couple. Stability simply does not exist here. The miracle of Gale-Shapley was never just the algorithm. It was the arena. Two-sided markets are special. merge the sides, and peace is no longer guaranteed by mathematics. Two columns of wishes. Propose, hold, trade up, repeat, and end in a silence that proves peace. Always stable. Startlingly fast. Bias toward the bold. The asking side takes rank 4, the waiting side takes rank 20. Honest for proposers, gameable for receivers, and fragile the moment the market loses its two sides. A theorem that was running hospitals before anyone knew its name, and has been running them ever since. Stability is a silence no one wants to break.